Okay, so in this video we're going to be talking about light. In the last video we talked about sound, and light waves and sound waves are completely different from each other. So we talked about how sound waves are longitudinal waves. We talked about the link between frequency and pitch, amplitude and loudness. Light is, like I said, completely different than sound. Light, first of all, I'll just write or underline this. Light is what is called an electromagnetic wave. Okay, so when we think of light, we typically think of visible light, what we can see with our eyes. But you need to understand that what humans can see with their eyes is only a very small part of what's called the electromagnetic spectrum. A spectrum is just like a range of things. Okay, electromagnetic, that's kind of a complicated term, but basically that means it has an electric part and a magnetic part. Okay, so there's lots of different types of electromagnetic waves along the spectrum, and light is only a very small part of it. Okay, so here's some facts about electromagnetic waves, which you also might sometimes see called electromagnetic radiation, but they are in fact waves. Okay, now everything I'm about to say applies for any type of electromagnetic wave, no matter where it falls along the spectrum, and then we're going to go through the spectrum piece by piece, just so you can understand, some applications and where you would actually experience these different parts of the EM spectrum on a day-to-day basis. Okay, so just some basic facts. Fact number one, all electromagnetic waves are transverse waves. Okay, it doesn't matter where they fall on the spectrum, all EM waves are transverse waves. Fact number two, all EM waves travel in a vacuum, travel at the same speed. That is the speed of light. Okay, so for example, a microwave and a radio wave travel at the same speed in a vacuum. That is the speed of light. Now, if you want to know how fast that is, that's about 3 times 10 to the 8 meters per second. Okay, or just to put it another way, and this is just down here, I'm just writing it bigger, 186,000 miles per second. Okay, so if you go into space and you shoot a beam of microwaves or a radio wave that's traveling about 186,000 miles per second, so very, very, very fast. In fact, nothing in the universe can move faster than the speed of light in a vacuum, as far as we know. That would violate laws of physics if that were to occur. Okay, so electromagnetic waves all travel at the same speed. That's something they have in common. All electromagnetic waves fall somewhere along the EM spectrum with a different wavelength and frequency. Okay, so there is a spectrum. Okay, they do have the same speed, but we've talked about before that we've talked about the wave equation before, and the wave equation says that the wave speed is equal to the wavelength, that's lambda, times the frequency of the wave. And so what I'm telling you is that as long as you're just in one single medium, the wave speed is the same for all types of electromagnetic waves, but you can have different wavelengths and frequencies. Okay, so in other words, the wavelength and the frequency can be any two values as long as they multiply together to give this number right here, because this is the wave speed for an electromagnetic wave, at least, again, in a vacuum. And I say in a vacuum meaning no medium, just because we talked about refraction before, about how wave speed changes when you go from one medium to another. So this value, 3 times 10 to the 8 meters per second, that's really the speed of electromagnetic waves, either like in space or maybe in air. The speed in, let's say, water or glass would be a little bit slower, but still pretty close to that. Okay, some forms of EM waves can be harmful to you, potentially causing cancer or other health issues. We'll talk about that later. And so these are just some of the facts about the electromagnetic waves that you need to know about. Now, again, light, what we think of as light, what we can see with our eyes, is only a very small part of the EM spectrum. Just for example, human beings cannot see radio waves. We cannot see microwaves. Okay, we can only see a very small part of the EM spectrum. I'll show that to you on the next slide. Okay, so pause it here if you need to write any of this down, and I'm going to erase this. Okay, so here is the EM spectrum. Okay, and before I go over it, I just want to point out there's two links up here. I'm going to post those up to you so that you can watch them. Just click on the links to open up those YouTube videos and check those out. They go into more detail about the electromagnetic spectrum, but here it is. Remember, a spectrum is just a range of values. And so this is what we call the electromagnetic spectrum, or the EM spectrum for short. Okay, just to save on time. Okay, and so starting at the highest wavelength on the left, I'm looking down here, and so I can see this is the highest wavelength. As we go from left to right here, we see a smaller and smaller wavelength because the waves get closer together. But we also see that the frequency goes up down here. Okay, and so we've talked about that before. That as wavelength goes up, frequency goes down, and vice versa. Okay, so the parts of the EM spectrum that have the highest wavelength on the left are radio waves. And then slightly shorter wavelengths would be microwaves, infrared, visible light. Okay, this is what humans can see. In the whole grand scheme of things, we can see it's only a very small segment of the total EM spectrum. Then ultraviolet, X-rays, and gamma rays. And some of you have probably heard of these before. Hopefully you've heard of at least a couple of these before. Hopefully you've heard of radio waves and microwaves. Ultraviolet is often called UV. Okay, so that we'll talk about each of these as we go through, where you might see them in real life. Okay, so let's start with radio waves. Radio waves are used for telecommunications. Okay, so cell phones. Obviously, when you listen to the radio in the car, those are transmitted using radio waves. These tend to be very, very long in wavelength. And again, they're mostly used for communication purposes, both here on Earth and if we want to beam signals to our satellites in space, oftentimes we would use radio waves for that. Okay, so that is on the far left side of the EM spectrum, the highest wavelength. Okay, now by the way, you don't need to know any of the specific values. You probably do need to know or be able to put the parts of the EM spectrum in the correct order. Okay, so that's why we're going through these in order. Okay, so after radio waves come microwaves, and Wi-Fi would kind of fall into that part of the spectrum as well. Okay, so I listed both microwaves and Wi-Fi. Obviously, microwaves, if you buy a microwave oven that uses electromagnetic waves to cook your food, that has a relatively short wavelength. If you, look inside a microwave, based off of its size, it gives you some idea of how small microwaves are. I would say you could probably fit, a couple microwaves inside a microwave oven, but they do tend to be pretty small, couple centimeters in general, at least the microwaves we use for cooking food. Next on the EM spectrum, and by the way, before I forget, there's a video I'm going to link down here about can microwaves cause cancer. We'll talk more about that later. I do want you to check out this video though, because it's kind of interesting and useful for you to know. The next part of the EM spectrum is infrared. Okay, so infrared, you might not have heard that before, but infrared is often used in thermal imaging, night vision, your TV remote. If you look at the end of your TV remote, you might see like a tiny little light bulb, and that light bulb oftentimes works in the infrared part of the spectrum. So you can't see it flashing when you hit the buttons, but you can see it if you have an infrared camera. Something you can do at home just for fun. A lot of the time your cell phone, the selfie cam on your cell phone, not for every phone, but oftentimes the selfie cam on your cell phone can see in the infrared. Okay, so if you're bored at home and you want to test this out, take out your phone, turn on the selfie camera, and then take your TV remote and hold it in front of your selfie camera and press some of the buttons. And when I do it on my phone, I can see the little light bulb at the end of my remote flashing. And I can't see it with my eyes, but I can see it with the camera on my iPhone, because for some reason the selfie camera can see a little bit into the infrared part of the spectrum. Okay, infrared radiation, we've said, and I've said this before, we perceive that as heat. Okay, so when we talk about infrared electromagnetic waves, we're typically talking about heat. All right. The next part of the spectrum is obviously the most interesting to us. That would be what we call visible light. That is what we can see. Everything from very red to very blue, and everything in between. Orange, yellow, green, blue, and then going on to violet. Okay. Visible light, what humans can see, is only a very small part of the EM spectrum. Okay. Some animals can see different parts of the EM spectrum. Humans can't see, very much past red or very much past violet. And so in the grand scheme of the whole EM spectrum, we can only see a small fragment of that. On the other side of visible light, okay, by the way, this is just like a blown up version of the EM spectrum, the visible light region. Notice, by the way, infrared has red in it. Okay, so infrared is right past red over here. Ultraviolet is right past violet on this side over here. Okay, so just to help you keep in mind the correct order of these things. Ultraviolet you might have heard of before. You also call these UV rays. You see these when you go to tanning booths. The sun gives off ultraviolet electromagnetic waves in addition to infrared and visible light. This is one reason why you might, put on skin protection when you go outside or you go to the beach to protect you from getting sunburn. That's caused by ultraviolet light. Okay, you also see these in black lights if you've ever gone to like a party where they have, glow in the dark clothing or people's like t-shirts are glowing. That's caused by black lights which emit ultraviolet radiation. X-rays, you should know what X-rays are for, typically used in medical applications. If you get X-rayed, that helps them see your bones or your teeth. If you go to the dentist, you might get X-rayed. And then gamma rays are typically come from radioactive material. And so that's probably not something you have a lot of experience with on a day-to-day basis. But a lot of materials that are radioactive emit gamma rays. Okay, so those are very, very low wavelength electromagnetic waves. Okay, now the last thing we're going to talk about, and we'll do one or two examples, but the last thing we're going to talk about is what's called ionizing radiation. And this is a term that's important, so make sure you understand what it's saying. So what it says in the notes, I'll just read it to you. It says EM waves from some parts of the EM spectrum have so much energy that they can cause ionization. Okay, so your first question should be, what does that mean, ionization? Okay, so ionization is basically where you remove electrons from an atom. Okay, so ionizing radiation refers to waves or particles that are capable of removing electrons from atoms. They have so much energy they can, hit those electrons, knock them off of the outside of atoms, therefore turning them into ions. That's why it's called ionizing radiation. Now, the reason that's bad, at least for humans or for living creatures, is because removing those electrons, depending on where the electrons are coming from, can cause damage to human cells and or DNA. Because if you think your DNA strands are made of atoms, and those atoms have electrons, and if you take some of the electrons away, you can cause bad things to happen to your DNA. Same thing with your cells inside your body. And that can cause anything from minor issues like skin death, skin damage. If you get sunburned, that's a very minor form of getting hit by ionizing radiation, because getting a sunburn comes from ultraviolet light from the sun. And so, that's a relatively minor thing. But you can also get more major issues from ionizing radiation. For example, you can get radiation sickness. If your cells and DNA become too damaged, they can, start causing issues like, cancers or things of that nature, or even death if you get exposed to enough radiation. On the next slide, we'll see how some parts of the EM spectrum are non-ionizing. That's not to say that they're completely safe for humans, but they are non-ionizing, and some parts of the EM spectrum are ionizing. And what we'll see is it really has to do with the wavelength of the specific EM wave that you're talking about. Okay, so pause it here read over this again. Make sure you understand what ionizing radiation is. There's lots of resources. You can look online or look on YouTube for ionizing radiation and why it's dangerous, and they can do a much better job of explaining it than I can. I do want to show you this though. Okay, so this graphic basically shows the different parts of the EM spectrum. And on the left, I've listed, what parts of the EM spectrum are non-ionizing versus ionizing. Let me make this a little bit bigger so you can see. Non-ionizing parts of the EM spectrum include radio waves, microwaves, infrared, and visible light. Okay, so in other words, the left part of the EM spectrum as we were going through. Okay, the longer wavelength part of the EM spectrum. Okay, so radio waves are non-ionizing. Microwaves are also non-ionizing. Infrared and visible light as well. Now, what that means is that a lot of people, are worried about microwaves giving you cancer. But you need to understand that based off of how much energy microwaves have, they just don't have the energy required to cause ionization. Now, you can be harmed by microwaves, but not because of ionization, because, for other reasons that I don't want to get into now. If you're interested, you can look up, why microwaves could be dangerous for humans, but they are a form of non-ionizing radiation. Forms of ionizing radiation: ultraviolet. This is why you put sunscreen on when you go outside so you don't get sunburned from the part of the sun emits ultraviolet radiation. And if it has enough energy, it can cause ionization in your skin, which is bad. We get protected from that from, like I said, sunscreen that we put on when we go outside, and also something called the ozone layer. If you've ever heard of the ozone layer, I don't want to get into how that works, but basically it's a part of the atmosphere that helps block out the dangerous ionizing ultraviolet radiation that's coming from the sun. It doesn't do a complete job, which is why we need sunscreen and stuff, but it does help a lot with that. If we did not have the ozone layer, we would be exposed to a lot more ultraviolet radiation, which would be bad for us. Also, X-rays. This is why whenever you go to get an X-ray, at the dentist or the doctor, they typically put like a lead vest over you to protect you, or to protect the rest of your body from ionizing radiation. And then gamma rays. I said that before, that you typically see those from certain types of radioactive materials. Okay, and so that's the different parts of the EM spectrum. I think I'm going to go ahead and stop here in the video. I know we went over a lot of information in this video. Please refer back to the PowerPoint. If you need more help, please reach out to me if you have any questions, or if you want any clarifications about different parts of the EM spectrum. And definitely check out the videos that I linked to you. Okay, so please let me know if you have any questions, and I'll see you in the next video.